You drop a piece of toast. It hits the floor, butter side down. Every single time. You write it off as bad luck. Maybe karma. Maybe the universe just hates you. But it isn't luck. It's physics. The butter side down effect is one of the few everyday frustrations that scientists have actually tested. Is it even real? Or does it only feel that way? In 1996, British physicist Robert Matthews ran a controlled experiment, dropping toast 300 times. The result? Butter side down 62% of the time. Random chance would predict 50%. A larger British study later repeated the experiment 9,821 times and found essentially the same result. So the effect is real. The explanation comes down to a surprisingly simple piece of physics. When toast falls from a table, it doesn't drop straight down. It rotates. The reason is that toast usually hangs slightly over the edge before it falls. As it tips, one side remains in contact with the table while the other side is already hanging in the air. Gravity pulls down on the unsupported side, creating a rotational force known as torque. The toast begins to spin. The crucial factor is table height. A standard dining table is about 74 to 76 centimeters tall. When toast tips over the edge, it starts from a nearly horizontal position, usually with the buttered side facing upward. From that height, the toast spends only about 0.4 to 0.5 seconds in the air before hitting the floor. During that brief fall, the toast rotates by roughly 180 degrees. A half rotation means the toast starts butter side up and reaches the floor butter side down. For the opposite result, the toast would need enough time to complete a full 360-degree rotation before impact. That requires either more airtime or a much higher rotational speed. Matthews calculated exactly what that would require. In his 1995 paper published in the European Journal of Physics, titled Tumbling Toast, Murphy's Law and the Fundamental Constants, he worked out the numbers. For toast to consistently land butter side up, the table would need to be approximately 3 meters tall, nearly 10 feet, about the height of an entire floor of a building. His analysis also showed that the rotational speed of falling toast is constrained by the way it leaves the edge of the table. It rotates enough to invert itself, but not enough to complete a full rotation before impact. For ordinary tables, those conditions create the same outcome again and again. Matthews received the Ig Nobel Prize for this work in 1996. The Ig Nobel Prize recognizes research that first makes people laugh, then makes them think. This study managed to do both. Many people assume the buttered side is heavier and that the extra weight pulls the toast downward. That explanation turns out to be mostly wrong. A typical layer of butter weighs only about 5 to 7 grams, while the toast itself weighs roughly 30 to 35 grams. The shift in the center of mass is too small to significantly influence the motion. The determining factor is the relationship between table height and rotational speed. The butter is largely irrelevant. The story also connects to a famous idea known as Murphy's Law. Anything that can go wrong will go wrong. Matthews argued that some situations genuinely contain a physical bias toward the unfavorable outcome. But psychology also plays a role. You rarely remember the occasions when toast lands butter side up because nothing important happens. When it lands butter side down, you notice it immediately. You clean up the mess. You remember the event. As a result, your memory exaggerates the effect. The actual number is about 62%. The number many people feel is closer to 100%. There is no practical solution. You cannot realistically build a 3-meter dining table, and you cannot change the physics of falling toast. In theory, increasing the spin rate or changing the way the toast leaves the edge can alter the outcome. In practice, that is difficult because dropping toast is almost always accidental. There is another reason this phenomenon appears so consistently in everyday life. Humans evolved to heights between roughly 1 and 2 meters, and the furniture we build reflects those proportions. Tables, counters, and shelves tend to fall within a narrow range of heights. That range happens to be almost ideal for producing the half-rotation effect. If humans were much taller, our furniture would be taller as well, giving toast enough time to complete a full rotation before impact. If humans were much smaller, toast would hit the ground before rotating very far at all. The famous butter side down problem is therefore not really a property of toast. It is a consequence of the size of the human body and the environment we have built around it. Every dining table, kitchen counter, and breakfast bar quietly recreates the same experiment, again and again and again. The toast is simply following the physics.